All right. So before I do chapter 22, I just like to go over vectors a little bit because I know there's been a whole summer between Physics 195 for a lot of people. So I just want to go over some basic things. Let's see here. So we have an XY axis, and a vector is just going to be anything that has a magnitude and a direction. So let's call this vector A. Vector A is going to have what we call a magnitude and some direction. Another way of writing vectors, if we have an XY plane like this, is vector A is going to be its
What?
X component.
Yeah.
Its X component, AX, I hat, plus its Y component, J hat. This is going to be the component of the vector AX. This is going to be the component AY. There's going to be an angle here. And the way we get our X and Y components of the vector is we're just going to do some trigonometry. So if I look at the opposite of this angle, that's sine of theta, which is just AY opposite over the hypotenuse, which is A. So that means AY is A sine theta. Same thing for the X component, but cosine. So cosine is adjacent over hypotenuse. So that's AX over A. If I multiply by A on both sides, then I get the X component of that vector is A cosine theta. So the reason this is important is you guys are going to be working with electric forces and electric fields. Those are vector quantities, and so they all can be written with a magnitude and a direction, and they can only be added together in X and Y components. So that's why it's really, really important to get this down. So I'm just going to put it here. If I wanted to talk about this vector A, which again could be a force vector, it could be an electric field vector, any of those things, it's going to have an X component, which is A cosine theta along the I hat, and that's also going to have a Y component, A sine theta J hat. If I have it in this form and I wanted to get the magnitude of A, all I have to do is the square root of the X component squared plus the Y component squared. And lastly, if I want the angle, theta, it's just going to be tangent -1 of AY over AX. So this stuff should be reviewed. That's why I went pretty quickly. But I just wanted to refresh you of what I'm going to be doing when I refer to the electric force as a vector and how I'm going to be treating it. You guys. Okay, cool. All right, that's pretty much all the background you need to know. So let's just get right into chapter 22. So first thing we have to know is we're working with charge now. So what is charge? So charge is just a fundamental property of particles. An electron has something we call minus charge. So minus charge goes to the electrons. Positive charge goes to the protons. Now, all we need to know is that charge is going to create force between particles. And we know that like particles, let's say a positive and a positive, are going to repel each other. And opposite charge particles are going to attract each other. So I'm going to put that here. like particles. Let me write that better. Particles of the same charge repel. So that'll be positive and positive, or negative and negative. If particles have opposite charge, they're going to attract. So particles of opposite charge attract. So that'll be positive and negative. Cool. So that's all we need to know about charge. There's something called charge. It's a fundamental property of a particle. We have a negative charge and we have positive charge. If our charge is the same, they're going to repel each other. If they're opposite, they're going to attract each other. That's all we know for right now. Now we can talk about this interaction, this repelling and attracting. What is that actually? So that's called the Coulomb force. I'm going to be referring to it as the electric force, but it's just the force between two charged particles. And let's just start with the magnitude of that force. It's F equals K, Q1, Q2 over R squared. So let's actually write it like this. Q2 over R squared. So it's really important to understand what this equation is actually saying. So first things first, we're talking about a force. So this is the force between two charged particles. Two charged particles. Because it's a force, it's going to have units of newtons, and it is a vector. So that means it has a magnitude, which is what I'm writing right now, and it also has a direction. I'm going over the magnitude and direction separately because, as I'll explain a little later, a lot of people get confused with these positive, negative charges and how that relates to a negative sign here or a positive sign here. So hopefully by the end of this, I'll make sure that you guys don't get confused on that. Either way, this is the Coulomb force. It's the force between two charged particles. It has units of newtons and it's a vector quantity. So it has x components, y components, all that stuff. This guy up here, K, this is referred to as the Coulomb constant. Coulomb constant. So it's just a number. Don't forget that it's there. It equals 9 times 10 to the 9 Newton meter squared per Coulomb squared. Make sure when you're writing your formula sheet and you write the Coulomb constant, write in those units because they might save you down the road. Okay, so F, force between two charged particles, K is the Coulomb constant. Now these here are charges. So Q1 is the charge of our first particle. Now for charge, it has a unit we call coulombs, which we denote with a C. And you're going to find in most of your problems that these are very, very small charged particles. So they're going to be in the order of nanocoulombs-ish. So Q1 is the charge of our first particle. Q2 is the charge of our second particle. Again, in coulombs. Now, I wrote these bars around the charges like that because what I want you guys to do when you do these problems whether it's a negative charge or a positive charge, you're always just going to put a positive number there. The reason being, let me sort of explain here with an example. Let's say we have, here's positive 1 nanocoulomb particle, and let's say here's a negative 1 nanocoulomb particle. Let's also say that they're 1 meter apart. And I want to know what the force is on this positive 1 nanocoulomb particle. So what is the electric force on the positive 1 nanocoulomb particle? So step number one for me is, let's see. Step number one for me is I want to decide, are these particles repelling each other or are they attracting each other? So I go up here and I see, oh, if particles are opposite, then they're going to attract. It looks like we have a positive, negative. They're opposite, so they attract. So I'm going to draw my forces like this. Now, once I have that information, I don't want to deal with the negative sign anymore. All the negative sign tells me of the charge, or all the sign tells me at all is this an attractive force or a repulsive force? After that, when I actually plug it into my equation up here, I'm going to leave it as positive. Okay, so I'm going to leave that there. If you have any questions about that, I'm going to do an example problem that may explain it a little bit better. But, okay, this down. Okay. And then just to finish up, our last guy here. So this is written with an R. This is not radius. This is just distance. Specifically, this is the distance from Q1 to Q2. Okay. It has units of meters. Again, it's very important that you put that in meters so that it cancels the meters in your Coulomb constant. That's how the units work out, and that's why it's really important to make sure you understand the units of the constant. All right, so that's our Coulomb force. It's the force that governs the interaction between charged particles. And again, all it says is if you have two charged particles, they're going to feel this force as K Q1 Q2 over R squared. That's it. Does anyone have any questions about that? I know that was a lot already. Cool. Okay. So again, I'll just put a note down here. We know the direction of the Coulomb force. By the type of charge involved. So are they like charges or opposite charges? Okay, there's Coulomb force. Now we're going to go to the electric field. So I like to explain that the electric field is actually a way of making these Coulomb force problems easier. So all it is the electric field is defined as the Coulomb force divided by Q. So that's all it is. And if I were to write out the Coulomb force, we know it's K, let's call it big Q little q over r squared, but then that whole thing is divided by little q. Those cancel, and we're left with k big Q over r squared. And this is the definition of electric field for particles. This is very important that this Coulomb force here and this electric field that I'm talking about are only valid if we're doing particle problems. If you see anything that doesn't have to do with a particle, you cannot use these. Okay, and again, I'm going to explain every term. This is our Coulomb's constant.
Wait, did you say it's only valid for particles for these
Yes,
equations? Okay.
yes. So you're only going to use these in a particle problem. All right, this is Coulomb's constant. Same thing, 9 times 10 to the 9 Newton meter squared per Coulomb squared. Q here is going to be the charge of our particle. So charge, and we're going to call it now something different. We're going to call it our source particle. Charge of source particle. The reason I call it a source is because now this particle is exerting an electric field. So it's the source of our electric field. Still has units of coulombs here for charge. Now this R, again, not radius, it's distance, but we need to define what that distance is. For the Coulomb force, that was the distance from your first charge to your second charge. So that's easy to understand. For the electric field, this is the distance from your source charge, big Q, to a point of interest. Point of interest. Again, that's in meters. What I mean by that is we have our source charge Q right here. And I want to define, let's say, the electric field at this point of interest. That means this R is going to be this guy right here. Distance between source charge to point of interest. And don't worry, they're always going to specify what your point of interest is for the problem. So just make sure when you are reading a problem about the electric field that you know immediately, okay, that's my point of interest. That's what I define all my distances are to. Right, last but not least, this is the electric field. We denote it with an E. It has units of newtons per coulomb, and it is also a vector, which means, once again, it has a magnitude and a direction. And we can define a net electric field and all that stuff. We can add them up. All right. So I'm going to do, now that you've seen electric force and electric field for particles, I'm just going to do a quick example just because I think it'll help with this stuff. Okay. So I'm going to draw an axis here. This is our y-axis and x-axis. I'm going to say I have a positive charge Q1, and let's call it 2 nanocoulombs. And then let's say it's a distance of, it's going to be at 0.5 meters, and 0. So it's 0.5 meters in the x. Now let's say we also have a negative charge up here. Let's call it Q2 equals 1 nanocoulomb with a negative. And this is going to be at 0 and 0.2 meters. Okay. So long story short, we have two particles, and the question is going to ask you, let's say, what's the net electric field in the center? What is net electric field in the center? So first things first, if we want to define the net electric field, we can actually start with the electric field from one particle and then add in the electric field from another particle. And one thing to note is our point of interest here, which we can call P. It's going to act as if it were a positive particle. All that means is now I know how to draw my electric field vectors. So if point P acts like a positive particle, that means it's going to feel an attractive force from this guy up here. So this is the direction of E1. It also means if it's positive, it's going to feel a repulsive force. Oh, that's E2, sorry. Sorry, I meant to say this is E2. It feels a repulsive force from Q1, so it wants it to go this way. So this is E1. So first step is always draw the direction of your individual electric field vectors. So at our point of interest, we got E2 pointing up, and we got E1 pointing to the left, hopefully. Okay. Once you have your electric field vectors drawn out, which is step number 1. So step number 1, draw individual E field vectors. And notice I only know where they point because I assumed that at the point of interest, it's acting like a positive particle. If you take anything out of this review session, that's probably the most important thing. So Sarah, you asked, why is it pointing to the left? Again, when you have a force problem, like this guy up here, it's really, really easy to decide what direction the force points because you just say, oh, this is a positive particle, this is a negative particle, okay, attractive force, they point that way. When it comes to an electric field, I want to know what the electric field is at the origin here, but I don't actually know, is that a positive particle there at point P or is that a negative particle? Because that's going to decide if the force is pointing whichever way it does. To get around that, in this class, we assume at point P that it acts as if it was a positive particle. With that assumption, which again is really, really, really important, I can say, oh, if there was a positive particle there, it would feel an attractive force towards Q2 and a repulsive force from Q1. So step number 1, draw individual electric field vectors from each particle that's in your problem and how it acts on your point of interest. And to do so, you assume point P is a positive particle. This is sometimes called in your class the test charge. It's not an actual charge, it's just a point of interest, but we assume it's positive for the sake of drawing the electric field vectors. Okay, that was step number one. Step number two is we want to find what is the net electric field. So we have our individual electric field vectors. How do we add them up? It goes back to how we add up vectors. So there's going to be a net in electric field net in the x, which is just going to be E1x plus E2x. All I'm saying here is the net electric field has an x component, and all it is the sum of the x components of E1 and E2. The net electric field vector in the y is just going to be the sum of the y components of the two individual vectors. So E1y and E2y. From here, it's important to decide what's positive and what's negative depending on how you define your axis. So here I'm saying up in the y is positive and to the right is positive. So for my x components, E1 is pointing in the negative x, and so it's going to have a negative sign. That. The E2 vector, this individual one here, doesn't have an x component, so that's 0. The E1y component is also 0, and E2y is positive since it's pointing up. So putting that all together, our net electric field vector is negative E1x I hat plus E2y j hat. Where when I say E1y, or E1x, sorry, I just mean x component of E1, which you might already see in this case is just the E1 vector, but this is just a good way of doing it to be complete. Okay. So step number one, draw the individual electric field vectors. Step number two, add up all your x components, add up all your y components, so that we're left with the electric field vector in component form. Now we can finally actually get to the physics part, which is using our E equals KQ over R squared. Yeah, page. So last step, finally we get to use this formula. All right. So again, we're trying to find the net electric field. That's negative E1 x I hat plus E2 y j hat. And a lot of you can already see this E1 vector is all along the x, so we don't even really need to note that it's E1x. And we don't even really need to note that E2 is E2y because it's all along the y. So I'm going to get rid of those. So this is I hat, j hat. Okay. Now the good part is we've taken care of the negative and positive signs of our charges by doing this first step. We've taken care of negative and positive signs for our vectors. And so now that we're using our formula, we don't need to worry about negative signs. Everything we plug in here is positive. So I'm going to start with E1. That's going to equal K Q1 over the distance between Q1 and our point of interest. So it looks like Q1 is 0.5 meters from our point of interest. So I'm going to put 0.5 meters squared. And just to be complete, Q1 we decided was 2 nanocoulombs. And again, I just put everything in as positive. Now going to E2, that's K Q2 over the distance from Q2 to our point of interest, which is this guy here. That's 0.2 meters. So 0.2 meters squared. And Q2 is -1 nanocoulomb. So this is where people get confused. They might put in that negative sign. Remember, we took care of the negatives and positives by saying, oh, they're attractive, they're repulsive, that's what they mean. Once we use it on that first step, we're done with it. We don't care about it anymore. So this step, we're just doing everything positive. So 1 nanocoulomb, 0.2 meters squared. And let me just to be complete here. So this is going to be 9 times 10 to the 9 Newton meter squared per coulomb squared times 2 times 10 to the -9 coulombs. Don't forget that nano is 10 to the -9. And then this is 0.5 meters squared. Same thing here. All right. So it looks like E1 is 72 newtons per coulomb in the I hat. And don't forget, we decided that this is pointing to the left, so it's negative. And that's what we did in step 2. The Y component of our net electric field is positive, and it's going to be 225 newtons per coulomb J hat. So now we solved the problem. That is the net electric field in the middle due to these two charged particles. Now, one thing is in his questions that are going to be on the practice test and on the real test, you're going to see a lot of problems like this, and I want you to go through it the same way. But a lot of times he wants the magnitude angle form. So just like I said all the way up here, you can write a vector as magnitude angle, or you can write it in component form. You're always going to use component form to get where you need to go, because that allows you to add up everything on the X, add up everything on the Y. Then we need a way of switching from component to magnitude angle. The way you do that is the magnitude of this vector is just the square root of the X component. So -72 newtons per coulomb squared plus the Y component, 225 newtons per coulomb squared. Notice I dropped the I hat and the J hat because the magnitude is just a number. It's a scalar. It doesn't have direction. It should be positive. So if we did 72 squared plus 225 squared and then square root that whole thing, That's going to be 236 newtons per coulomb. This is going to be the magnitude of the net electric field. Any questions so far? Okay. So I'll leave it for you, but then you'll also find the angle. And remember, that's just tan -1 of EY over EX. So that was an example just to show you guys how you would do a problem like this. Obviously, you're going to have to practice on your own to get good at it. But these type of problems where you have particles and you're finding the electric field at some point, or you're finding the force between particles, that's pretty much, if you know that stuff really, really well, that's like 70–80% of the exam right there. So just drill these type of questions as hard as you can because it is a quick test and you got to be really, really good at understanding how to find the electric field, how to find the electric force between a group of particles. Cool? Okay. All right. So that was E field. Um, the electric field and the force are pretty similar. Do you guys also want to see an example of finding electric force, or should I just move on? Ooh, okay, split. You know what? I'm gonna move on, but I'll post some separate example problems. How about that? Okay, so chapter 22 is pretty much all Coulomb force, electric field. Here's our example. I'm just gonna end with the very end of the chapter, which is insulators and conductors. He does do maybe one or two problems on this, usually on the test. So I'll tell you what's particularly important. So for insulators and conductors, basically, we split up all materials into these two categories. They're either an insulator, which just means that their electrons are stationary, and therefore do not move freely. Oh, and for Peyton, there is not partial credit for showing your work. It's really unfortunate. Okay, insulator, electrons are stationary. Conductor is just another class of materials, and that's all the materials where electrons flow freely. Freely. Okay. Have those definitions somewhere. I'm going to show you the consequences of what that means. So there's something we call charging, and that's where you take a neutral object and you give it a net charge. So charging, take a neutral object. It can be a conductor or an insulator, and give it a net charge. And that can be either positive or negative. There are a few ways to charge things. Number one, you can charge an insulator by rubbing. Note, you cannot charge a conductor by rubbing, only an insulator. The reason for that is when you rub an insulator, the heat is going to break the bonds that keep those electrons stationary. So the heat's going to break those bonds, and then that's going to release those trapped electrons. Electrons. And then you get your net charge object. So what that looks like, here's a neutral conductor. It has a bunch of positive, negative charges flowing everywhere, but it's net neutral. We're gonna rub it. And then once we rub it, we're gonna release electrons and we're gonna give it a net charge. Let's say we give it a positive charge. All right. So that's the first way to charge an insulator. Not going to be a whole lot of questions on it, but you guys need to know it. The more important stuff is something called polarization and charge by induction. Charge by induction. Induction. This is something that you might actually get asked on for the test. So what polarization is it's an electrical phenomenon of conductors. So we have a conductor here, and its charges are moving freely. And let's say we bring let's say we bring a charged insulator really close. And let's say this is a positive insulator. So as this charge object gets really close to our neutral conductor, so here's conductor, here's insulator. As our charged insulator gets close to our neutral conductor, the electrons are going to start to feel a pull towards this positively charged insulator. So they're all going to group really close to it here. And then since all these electrons have moved over to the insulator side, that's going to expose a net positive charge of the protons on this side. So what happens is, this is called polarization. So notice if I take the insulator away, this phenomenon is going to stop. All the charges are going to re-spread out and we're going to have a neutral conductor again. But for that brief period of time, we've basically polarized the conductor. So that's what this phenomenon is called. It is important, so make sure you understand this and have it somewhere in your notes. With polarization, there's something called charging by induction. That's when first we polarize a conductor. So we do it just like this. And then we take another large conductor and we touch it to this guy. We take another large conductor and we touch the two. And all these electrons that we polarized are going to flow to this conductor, spread out evenly. And then when we take it away, we're left with a net positive conductor because we polarized everything, all the electrons went on one side, and then we took all the electrons away with another conductor. Once we take the conductor away, the insulator away, everything, we're left with a net positive conductor, and this is called charge by induction. Do you mean electrons flow away from the conductor towards the insulator? No, I mean they flow towards it. So you may have seen other examples where the insulator is negatively charged. Totally the same example. I just went with a positive insulator as just a random choice. And because it's positive, electrons are going to feel an attractive force. Because electrons are negative, they want to move towards a positive charge. So that's why they move towards it. But you may have seen in class, he may have used a negatively charged insulator for the example. So that could be okay. That's that. There's one more important point, and it's the most important point for insulators and conductors. And it's probably, he usually asks a very similar question from year to year. But all you got to know is that charge in a conductor spreads evenly on the surface. This is a property of conductors. It's something that we just know from experiments, and it ends up having some really important, uh, it ends up being really important in certain problems. Peyton, you asked, yes, I mean the electrons are flowing away from the second conductor. Yes, they are. Sorry. Okay, put this in a box. So all I mean by that is if a conductor has charge, all that charge, whether it be electrons, or whether it be positive charge, negative charge, it's all going to be along the surface and it's going to be evenly distributed. Okay. Okay. As a quick, super quick example, I know we have to keep going through it. One question that the book tends to ask is like, we have a charged sphere here. It's a conductor. It has a charge Q1. We have another conductor here. It has charge Q2. It won't give you what Q1 and Q2 is, but it may say something like the total charge of the system is, I don't know, 10 nanocoulombs. And it'll say, what happens if I touch these two objects together and then I pull them apart? So we know that Q1 plus Q2 equals 10, but we don't know, does Q2 have 8 and Q1 have 2, or how it's distributed. We know that if they touch, then the charges are going to flow between them. And the total 10 nanocoulombs is going to evenly spread along both of them. So that now if I pull them apart, if Q1 and Q2 are identical as far as surface area goes, then Q1 now has 5 nanocoulombs and Q2 has 5 nanocoulombs. So they've basically split the total charge. That was a really quick example, so if you don't understand it, it's okay. But just know this is something that he likes to ask, and it has to do with this property that conductors spread charge evenly over their surface. Cool. So that is the end of chapter 22. All it is insulators, conductors, the electric field of particles, and the electric force of particles. Does anyone have any questions? Or go to 23? Oh, good. Okay. Right. Just put this in. So I'm going to be honest. Will all the problems be number based or some be conceptual? A lot of them are going to be number based. Maybe like one or two are conceptual. I don't have the exact a number that's conceptual though. I'm sorry. Okay. So moving on to chapter 23, I'm going to be honest. Most of the physics is chapter 22. Chapter 23 is more of a plug and chug situation. So we're moving out of the realm of particles and into the realm of objects. So there's going to be a lot of integrals and stuff like that in your textbook. You're not required to do an integral one time. And I don't really like how the textbooks lay it out because it makes it seem like you have to do an integral. You do not have to do an integral for this class. You only need to know the final equation for an electric field for each individual um, electric distribution or object. There are only four objects, or five, sorry. There's a point charge, an infinite line of charge, a disk, an infinite plane, and a dipole. Those are the five objects. They have five very specific equations that you use when you see an object. So what I'd recommend is I'm going to give you the equations and I'm going to explain how to use them and what each point is. I'd recommend you just put these on your equation sheet and make sure you practice with them. So starting with the electric field of a point charge, we know that it's just E equals K Q over R squared. Q is charge, R is distance from Q to our point of interest, point P. That one's pretty easy. All of chapter 22 was basically that. Now, an infinite line of charge. This is one of the most popular ones. So you're more than likely going to see it on the test. An infinite line of charge is going to have infinite length, and it's just going to be a bunch of charges, either positive or negative, that are in a line like this. Okay. Yeah. So the equation I'm going to write is for our point of interest here. Again, we always define what the point of interest is. So this is our point of interest P. It's going to give us the electric field here. And that's going to be at a distance R above our line of charge. So this is R. So the equation for an infinite line of charge, again, this is something you're just going to put into your formula sheet, is just E line, again, it is a vector, is K times 2 times lambda, which I'll explain, over R. This is just electric field. It is a vector, so you can add up the electric fields from multiple lines of charge. It's still going to be in units of newtons per coulomb. K is still just our Coulomb constant. So our 9 times 10 to the 9. Now this lambda here, this is referred to as the linear charge density. This is something that is going to be given to you in the problem or something you're asked to find given the electric field. Technically, it is defined as the amount of charge per unit length, where length is the length of this guy here. Remember, this is an infinite line of charge, so it has an infinite length. That's why we're able to talk about a linear charge density, so charge per unit length. But again, when you do a problem, it's going to give you this is the linear charge density. You plug it into your equation there. And it has units of Coulomb per meter, linear charge density. So this R, again, you have to be very, very careful about your definitions of R. They change for every equation. In this case, R is the distance from your line of charge to point of interest orthogonally. When I say that, I mean that you can see that we define the distance at 90 degrees to the infinite line of charge. And again, that's in units of meters. Okay, so that's line of charge. Write this equation in your formula sheet. Understand what each piece means. That way, when you go to a problem, you can say, okay, this is a line of charge. This is the formula I need to use. This is how I define R. This is what linear charge density is, all that. Pretty much, Peyton. Just think of it as you could think of it like the bisecting distance is another word some people use for it, orthogonal distance. I tend to think of it just as the height above the infinite line of charge is easiest for me to think about it. Cool. Disk of charge. Again, I'm going to give you the setup. I'm going to give you an equation, put it on your formula sheet. Chapter 23 is it's really plug and chug. So if you ever encounter a disk of charge, it's going to look something like this. It's going to have some radius r, and there's charges dispersed throughout it. So if I want to find the electric field at point P here, at some distance z above the disk of charge, then my equation is the electric field of the disk is neta. Going to explain what that is. Over, I'm just realizing this is a terrible equation to put in here. 2 epsilon naught. I'm going to explain that right now. 1 minus z over square root z squared plus r squared. Okay, super ugly. You don't have to remember this. I never do. Put it on your formula sheet and make sure you understand each term. This is the electric field due to a disk. It's in units of newtons per coulomb. This guy here, neta, this is the surface charge density, another definition. It's something you'd be given in the problem. All it is an amount of charge per unit area. So units of Coulomb, meter squared. Epsilon naught. You've probably seen this in class. It is another constant. I'm sorry, there's so many. This is called the permittivity of free space. Again, something to put on your formula sheet. Permittivity of free space. It is 8.85 times 10 to the negative 12. One thing I want you guys to note about epsilon naught here is our Coulomb constant K is actually defined as 1 over 4 pi epsilon naught. So that means the same thing. If you were to get into, let's say, upper division physics, which I know a lot of you are just trying to get through this, like for engineering and stuff. If you were to move on to further classes, we only use 1 over 4 pi epsilon naught. and you understand where it comes from, why it is the way it is. For the purpose of this class, Coulomb constant K is easier to use. But just know epsilon naught, 1 over 4 pi epsilon naught, same thing as saying Coulomb constant K. They're just two constants. And by the way, I'm showing you this disk of charge equation. I have never seen him actually put a disk of charge on a test. So put this somewhere so you have it, but don't stress out about it, especially since it's the ugliest looking one. Just to finish out, Z here is distance from disk to your point of interest in meters, and then R is just the radius of the disk. Again, put it somewhere, understand each of the terms. It's not great. Yeah, so surface charge density, you will see this, especially a little later on. All I'm saying is this is a new concept that we call surface charge density, and we define it as the charge per unit area, which has units of coulombs per meter squared. For the sake of this first test, way more important that you understand linear charge density. And by understand, just know what it is, know that it exists. And if they give it to you in a problem, you know where to put it. But surface charge density isn't something you're going to see too much until you go to the next test. But just be aware of it. Yes, pretty much. Charge over a surface. Exactly. Linear charge density is charge over a line. Surface charge density is charge over surface. You're also going to see later on there's charge over a volume. Not right now, but anyway. Okay, so that's disk. Next, really important one. Disk wasn't that important. Line is very important. Electric field of a particle or a point is very important. Infinite plane is the next very important one. It's one that's more than likely going to be on the tests. Do, 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 do. So I'm going to draw, this is our infinite plane. It's going to have a bunch of charges here. And I want the electric field at a point P above our infinite plane. Okay. So again, this here. The electric field from a plane, so I'm going to call it E plane, is neta over 2 epsilon naught. So I lied. Neta actually is going to be important for you here. And again, neta is the surface charge density. It is something, once again, that you will be given in the problem. It will say the surface charge density of this infinite plane is this, which is again why I have it defined. It's charge per unit area. It's in coulombs per meter squared. So when they give it to you, they're going to say the surface charge density of this infinite plane is 3 coulombs per meter squared, something like that. And then you say, okay, I'm going to put that in the top here, divide by 2 over epsilon naught. So say, again, epsilon naught here is a constant. It's just 8.85 times 10 to the negative 12. And this is just the electric field, units of newtons per coulomb. One thing to note about infinite planes that is really cool is that the electric field isn't dependent on how far above the plane you are. So you'll notice this electric field just has surface charge density and another constant. So it's pretty cool. There's no Z dependence here or R dependence. Doesn't matter how far we are above the plane, doesn't matter how close we are to the plane, it's going to be the same electric field. So no distance dependence. Just a note, it's pretty cool. And it's why capacitors work. So yeah. All right. Last of the five distributions is going to be the electric dipole. A dipole is just two equal but opposite charges in proximity. So let's call this plus Q and minus Q. That's all a dipole is. What does A represent in surface charge density? Oh yeah, let me just. A is area. More than likely, by the way, you're not ever going to have to calculate surface charge density. They're just going to give it to you. But I just want you to know that that's what the definition is. It's charge per unit area. Okay. Dipole is two charges equal but opposite. There's going to be a distance between them that we call S. We just decided the distance between them is S. I don't know why, but okay. We're also going to define something with our dipoles that's special. It's called the dipole moment. It's going to be a vector, and it is QS vector. So let me explain that a little bit more. So P is our dipole moment. It has units of Coulomb meters, and it points from our negative particle to positive particle. Now, these are all definitions. This is just something we decided, so write it down somewhere. We just decided there's something called the dipole moment. It points from the negative particle to the positive particle. And it has units of coulombs times meters. Okay, that's our dipole moment. And S, just to remind you, is the distance between the particles, our two particles here. Okay. So there's going to be two equations for a dipole, and it depends on if we want on axis or what's called bisecting. This would be the bisecting electric field. I call it EB. This would be the on axis electric field. I call it EA. The equation for an electric field of a dipole on the axis. So again, this is the electric field due to a dipole on axis, newtons per coulomb again. This is a vector. Is just going to be negative K times 2, our dipole moment, over R to the third. Now again, we got to understand what each one of these terms is. The negative sign is just in there, leave it in there, understand it later. K is our Coulomb constant, per usual. P is our dipole moment. And then R is going to be very special again. It's going to be the distance from our point of interest to the middle intersecting point of our positive and negative charge to center of dipole. So that's what that R is. Now for our bisecting electric field, it's going to be negative K B r to the third. It's very similar, but we just dropped the two. That's dipole moment in Coulomb times meters. And then again, this is the distance from your point of interest to the middle of the dipole. And let me just, yeah, I'll scroll up real quick. Yeah. So that's dipole. Do To answer your question, Christian, would this give the same answer if we use the equations from the previous chapter? Yes. So if you use the equations from the previous chapter and you just said, these are two particles, I want to know the electric field due to them, you can totally just use your chapter 22 stuff and you'll find the same exact thing. Now, this is just if you have a dipole and they'll specify in the problem, this is a dipole question. Usually they're going to give you dipole moment and they want you to do it this way. So that's why it's good to have the equations because they may not give you certain things you would need to use your chapter 22 stuff. Let's see. And that's it. So chapter 23, I do apologize. It's mostly just plug and chug. You just need to understand that there are five different electric field distributions. They each have their own equations, but at the end of the day, you're just finding the electric field. So, any last minute questions? Because we're pretty much up.
What
Would that
about
work?
the sorry, what about the with like a pole and then you're only trying to find like a certain distance on the pole or rod?
This up here?
I'm looking at the slides right now from the lecture, and he has like
Uh-huh.
a horizontal rod and
hmm
then only like a certain portion of the rod highlighted that he wants to find.
Okay. That is. mm, That could be if I know if you're talking about this, there is a non-infinite line of charge. It could be that. That is a separate equation. It's I will say not something I think you're going to be asked on the test. On the test, he usually just does infinite lines of charge. But let me see where that is. Is this sounding like what it is, or am I way off?
Yeah, I think that's what it is. Yeah, I have the
Okay.
equation. I was just wondering if you think it's gonna like be on the test or anything. All right, it's on the
Oh, okay.
slide, so
I gotcha. Okay. I'll just since I know the equation, I'm just gonna say in your book, yeah, it has the equation for a non-infinite line of charge. Um, he always puts infinite lines of charge. I'm willing to bet you're not gonna see a non-infinite.
okay, thanks.
Yeah, but still put it on your equation sheet because you never know. For Sarah, yes, I'm gonna upload some force example questions. I'm just gonna give all this to your professor to send to you. Hopefully, he'll send it out later tonight. See. Kyle, why does blah blah blah? Let's see. Oh, difference between EA and EB for the dipole moment. EA is very specifically called the on-axis electric field. It's on the axis of the dipole, whereas EB is going to be the electric field that bisects the dipole. It's just weird definitions. That's the only difference. Ring of charge instead of a disk. So that's the thing. A ring of charge is another thing like the non-infinite line of charge. It is in your textbook. You should write it on your equation sheet. Not something I would worry too much about being tested on. But that's why I just showed you guys the really popular ones. Yeah, it's gonna be uploaded. Does anyone have any other questions?
Do you know if we can like label the equation or the equation stuff for the formula sheet?
I don't see a problem with that, but I'd probably just go with exactly what he has on his um syllabus, honestly.
Okay, thanks.
Mhm. Okay, if there's no more questions. Yeah, I'm basically gonna upload this recording and upload the notes we took, and I'll upload some of those problems to your professor, and then he should send them by the end of the day. So thank you guys so much for coming. Appreciate it. Good luck. You got this.
Thank you.
Yeah.
Yeah, thank you. Thank you so much.
Mhm.
Thank you very much.
Thank you.